Electric field strength due to a point charge at a distance is our agenda. I need to find that. Can you see there is a yellow charge and there is a blue charge? There is a symbol Q, there is a symbol Q naught. One of them will be the source charge, the one who creates the electric field. And the other one would be the test charge, the one who happens to be in that field. Which charge is the source charge? Which charge is the test charge? Actually, it's your choice. But I am mentioning convention here. Conventionally, the subscript naught, Q naught, the blue charge, is the test charge and small q is the source charge. So the problem statement has changed. What are we trying to do here? I am trying to find out electric field due to a point charge Q at a distance R. Is the question clear? Let's go on. What is the expression of the force on this test charge Q naught? It is Fe equals 1 upon 4 pi epsilon Q naught by R square. Don't forget, this is your test charge and this is your source charge. Whose field are we finding? Q. Who are we using it to find? Q naught. So, step 1, you found the electrostatic force of interaction between the two charges. The expression is on your screen. 1 upon 4 pi epsilon Q naught by R square. Can you see an arrow pointing radially outwards? F subscript E bar. Got it? In fact, I could have put this charge Q naught anywhere on the boundary or circumference of this circle, isn't it? Incomplete? Why circle? Sphere. If Q, the source charge, is at the center, at the pivot, my radius vector R could I actually move in all possible 3D directions, right? In fact, I could have drawn a sphere of radius R because every point on the boundary or the periphery of the sphere is actually equidistant from the center where the source charge Q is kept. What I'm trying to suggest is that the expression of force, magnitude, not the direction, the magnitude of force between these two charges would remain unchanged if this test charge could move anywhere on the boundary of the sphere. Right? Perfect. Look at that step 2. Focus closely. Look at the color sensation. Did you see this light yellow broadcast? I'll do it again. Look at this light yellow broadcast coming from small q and going on to Q naught. What is this yellow broadcast? It's actually like field. Starting from the source charge Q and Q naught. Is Q naught happening? Is Q naught inside the yellow zone of influence? Yes, it is. Is Q naught in the field of Q? Yes, it is. And it experiences a force. The moment we have been waiting for. Electric field magnitude at R is defined as E equals Fe upon Q naught. What's left? 1 upon 4 pi epsilon Q by R square. So the magnitude of electric field of a charge Q at a distance R is 1 upon 4 pi epsilon Q upon R square. Right? Question. It's a vector. Agreed? Is this field produced by point charge Q a uniform field or non-uniform field? Well, look at the beautifully symmetric diagram of a circle or a sphere actually. Right? If I'm able to draw a beautiful uniform diagram and the field value is same at every single point, the field is uniform. Wrong. Electric field, just like electric force, is a vector quantity. Yes, the magnitude of electric field at every point R away from the Q is same. 1 upon 4 pi epsilon naught Q by R square. But the direction is radially outwards. Can you see the number of arrows? Are any of these arrows in same direction? No. All these arrows are pointing away. So what kind of field does a point charge produce? Non-uniform electric field. It's a catch, okay? This is the mistake. This is a trap. This is a pitfall you should be aware of. The nature of electric field produced by a point charge is non-uniform in nature. And what's the formula? The formula is 1 upon 4 pi epsilon naught q by r square. Hey, where is the direction of this electric field? Well, you divided the force by q. The direction is exactly like the force, radially outwards. The field produced by a point charge is non-uniform and radially outwards. Good. 1 upon 4 pi epsilon q by r square. That means the mathematical variation of electric field strength with r distance is inverse square law.